Hello and welcome to my third video on registers. This one we are going to go over a microprocessor that I have shown here. I'm given a series of questions and I'll go ahead and answer all these questions, and we can kind of move our way starting from the top. So first I'm going to explain the structure of the microprocessor and kind of show off the regions and sort of what everything does from a more macro level. So up here, this is called I guess you call it the processing unit. This is where, so we have all these modes here, and that can be performed by this ALU Mini right here, and this is just it does a bunch of different, it has a bunch of different functions. So if you're in mode 0, it'll subtract 2 values. If you're in 1, it'll add, and so on and so forth. They're all kind of described here. And all of that is sort of done in this quadrant here, or I don't know, a quadrant, but section. It stores the values that are to be added or performed actions upon. It does those actions, and then it controls when that output is able to be accessed by the rest of this machine. The other parts of the machine are, this is this section here with all these RAMs and ROMs. This is the sort of memory holding location, I guess. This is where we read and write things. This is where we store information. This is where we put information onto the data bus. And yeah, so we store things, and then we also can and put things on the data bus. And I'll explain what the data bus is later. And then lastly, we have kind of the control area for this entire thing. This is what we touch as users, and this is what a controlled, if we had a controlled microprocessor, this is what the controlled part of that would do. It would make decisions like all of these switches here. The control part doesn't necessarily have a section, I would say. You could say it's the clock read and write area, but it's also, this switch right here, A or B, enable B, choosing the select mode, although I suppose that would be necessary even on a controlled microprocessor, but regardless, this enable accumulator out, all of these little switches here that are chosen by the human being operating this microprocessor is part of the control unit. And I would say that those are basically, those are the three main components of what we're looking at here. And next I'm going to demonstrate 10 times 2, how we would perform that operation on this thing here, or on this microprocessor here. And now 10 times 6, that's 60. You can't represent that in 4 bits, so we're going to have see, this is why we have this mult ls4 and mult ms4 operation. This is the least significant 4, this is the most significant 4. So instead of turning that into like hexadecimal or something, what we're going to do is we're going to have a binary output, and we're going to first find the least significant 4 bits of 10 times 6, and then we're going to find the most significant 4 bits of 10 times 6, and then we can just sort of read them across. And I've already kind of done that here. I was just warming up for the video, but and so that's why I have everything loaded up ready, but we can kind of restart from the beginning, and go from there. We can show how we got 3C, which is the hexadecimal value for 60. Sorry, I'm a little tired. What we can do is we can go into read mode, and that's so because the read mode, first we're going to have to load this value into this B register here, because what we do is we first load a value into B, it's remembered, and then we load a value into A, and then we can perform the operations. So first we have to load that initial value into B, which I'm going to say is going to be 10. In this case, it doesn't matter. We could do 6 if we wanted to, but we're going to do 10. And so what we have to do is we have to be in read mode, and we want to read. Oh, that's kind of weird. Oh, that's because this accumulator is on. Oops. Okay. So we want to go into read mode, and we want to read ROM 0. And because of like the nature of this decoder, this is plugged into ROM 0. This is 0 with slot, and so 0, 0, 0 represents ROM 0, and then we want to read what's on ROM 0, which is the value 10. And so now we want to take this value 10 and we want to load it into B. So this is A right here, see, because it's going into the A port on the ALU Mini, and this is B because it's going into this register, which is then connected to B on the ALU Mini. So we want to make sure that we're loading this into B, and we can swap that here if we'd like. However, it was already on B, so we'll leave it as that. And then we want to enable this register to be able to read values. And then lastly, we just want to load this value in by doing the clock pulse. Now it's already in there, but we'll do it again, just to show if I loaded that in and this were a different value, it would work. And so now we have that value into B. So now we want to make sure that A is the right value, because we have 10 loaded into B. However, there's still a 10 here. We need this to be a 6. So what we want to do is we see that 6 is loaded onto ROM 1. So we want to make sure that 1 is being loaded onto the data bus, or 6 is being loaded onto the data bus, the value from ROM 1. And so now you can see this value up here has changed to 6. But it's being loaded into B. Not yet, because we haven't actually activated. We haven't given this register the right conditions to actually accept that value, but it's trying to go into the register, and we actually want that to go onto this line here. So we want to flip the switch. That swaps this over to A, and so now we have a value for B and we have a value for A. So now we can perform our operation. And so we can do either first, but let's start with operation 2. That is going to give us the least significant 4 bits of this number. Okay, and it's outputting 1100. Those are apparently the least significant 4 bits. And now we want to load this onto our accumulator. Now it's already there because I did this before, but if I wanted to do that, I can just do the clock pulse, enable it, and then it would be there. I want to unenable it, and now this value is just sitting in limbo right here. It's waiting for this accumulator out to be active to actually do anything. And well, now we can do that, but we have to make sure that we're not reading, because if we turn this on, it totally breaks everything. So we need to make sure that we're not doing that. And the way to make sure that this value is actually onto the data bus is we need to go into write mode. So now that value 6 isn't interfering with this. See, now this is undefined, and we want to now load the data bus with our value that we generated from our ALU Mini, and then we want to load it into whatever RAM register we'd like. In this case, I'm going to choose 6. Now the value's already there, but we're just going to do it again. So we have to choose RAM 6 here. So that's given by the value 110. And as you can see, it goes over to RAM 6. It's enabling it. And now we just need to turn this on. See, now this value is loaded onto the data bus, and we just need to do a clock pulse. And what that does is that's going to load the value 1100 into this register. Now, to show you that it's actually doing what it's doing, or what it should be doing, I'm going to load an incorrect value into RAM 5, because that's where I'm going to put the most significant bits, but I'll just do the least significant bits just to show you that it's actually doing it. See, that changes to C, and that's what we have in RAM 6. So it's loading that value properly. And now I'll just quickly do the next part. And we don't need to change much. All we need to do is read 6 again. And we're just going to get the most significant 4 now. So I'm going to turn that off. I'm going to go back into read mode. I'm going to read the first one, because we already have, like, 10 is still in the B register, so we don't need to do that again. So now this is an A, and now we can perform our function. We want to do 3 this time, 0011. We want to enable this. We want to tick the clock, 0011. We want to unenable that. We want to go into write mode. We want to select RAM 5, and then we want our accumulator out to be on, and then we want to pulse the clock, and boom, now we have that 3 value again. That gives us 3C, 3 being the most significant, C being the least significant, and 3C in hexadecimal is in fact 60. And so yeah, we can actually Google this right now. We can say, what is 001100 in binary? I obviously already looked this up. And it gives us 60. We could have done that computation ourselves, but we got the internet for a reason. So yeah, that is 10 times 60 on our microprocessor. And now we can go over what the databus is. You might have already been able to deduce what it is based on what I've said thus far. But we can just go over it anyways. The databus is this big black wire here. And what that's doing is this databus can only hold one value at a time. And it allows the entire microprocessor to basically communicate. Without this databus, we wouldn't be able to give any of our registers what our output is. Nor would we be able to read any input that we have from any of our read-only memories. So it just allows the entire system to communicate with itself, basically. Let's see here. Okay, so it says, why is it useful in a microprocessor to only allow register changes to occur at narrow, regular intervals on positive clock pulses? Now, I don't think that there would be any problem if it were negative clock pulses. You would just have to do everything inversely. So every positively edge-triggered thing would have to become negatively edge-triggered and yada, yada, yada. But it's easier to just make them positively edge-triggered, because then we don't need to add a NOT gate. But if so positively it's triggered, and then they have to be narrow, which I would assume means fast in this context. So very rapid clock pulses, and that's just so that whatever values that we're working with are actually stored into data, and not the clock pulses happen fast enough such that if we input a value, it stores that value before we can change it. That way we don't change things too quickly and then values are skipped over. For example, say that I want to read this into, say, this B register here. Say that if the clock pulse was super slow and this enable port is on, and I want to say, okay, let's load in 10, and then, okay, so I would assume 10 is loaded in, so we'll change it. We'll do this. Oh, but now the clock is ticking. And now an incorrect value is loaded into that. Well, this would have to be off, but now an incorrect value is loaded. Oh, but I thought 10 was loaded. Oh, but the clock was too slow. That's a kind of elementary example, but we need them to be fast so that things are saved properly and that we're not skipping over values that we intended to put in our system. Let's see here. It says estimate how many gates would be contained just in the ALU and discuss the value of hierarchical design. So I did look at this a little bit. The ALU Mini, we actually have it right here. So it's got like all of these devices. It's got the LB Mini, it's got 4 muxes, it's got a bunch of arithmetic functions here. And the LB Mini, it has 4 gates and then it has 3 muxes itself. Each mux has like, I think it's like 7 gates or something like that. So that's, 25 just here. Let me go to ALU, and so we have 25 literally just right here, and then we have like 28 right here, 7 times 4. So that's like 53. And then we have all of these here, which probably have like, I don't even know, but let's be conservative and say 10. Or I guess we could say 7, just like a mux. Probably more than that, but let's just say 7 for experiment's sake. So that's another 21. That's what is that? 74. So that's 74 gates right there. And this circuit, that just goes to show that this circuit is absolutely enormous, right? All these registers have a bunch of flip-flops, and all these flip-flops are made out of gates, and it's just crazy. And then the value of hierarchical design, and I looked this up because I wasn't totally sure what hierarchical design is, but I'm assuming it just means that like a multi-layered design almost. It's designing reusable components such that we can create emergent circuits out of them. So basically, to use this circuit, we don't need to know how the ALU Mini works. We don't need to know how many gates it has. We just can use it as a black box. We just know that the ALU Mini, that if you put it into this mode, it's going to output the subtracted values or the multiplied values or the added values. And so the value of hierarchical design is that it simplifies everything so much for us, and it really it emphasizes maybe it simplifies the circuit so much that you can actually see what it's doing, what its meta functionality is supposed to be, not what is actually internally happening. If we saw all 80 or whatever, however many gates are in this ALU Mini actually on the screen right now, the circuit would be so confusing that we'd probably get lost in it. But the fact that it's just put into this nice, neat little box that's labeled and has a title on it, it makes everything a lot easier for us to understand. Because at the end of the day, we're people, we're not computers. And we need things to be abstracted in particular ways. Alright, and that's it for this R3 video. A little bit of a longer one, but like our professor said, this is the culmination of this entire class, basically. So I hope you enjoyed, hope you learned, and I'll see you in the next video. Thank you very much, and y'all have a great day.